Hello, my name is Toru Yagi. I'm from the University of Tokyo, and today I would like to have my presentation, which is about the investigation of pathway formation mechanism in fracture toughness test over the joint and the improvement of acceptance criteria. Here is the contents for this presentation, and I will firstly talk about the introduction of my study. During the CTOD test, which measures the fracture toughness of steel material, sometimes a phenomenon which is called popping occurs. Alright, so popping is an arrested brittle crack. It manifests itself with a drop in load and increase in clip gauge displacement. And here is a clip of a CTOD test that involves popping. That graph is a PVZ curve, and right now popping occurs and fractured. Alright, so when popping occurs during the test, let's say if that popping is judged as a fracture, the fracture toughness of a material is measured by point A on the PVZ curve on the slide. And let's say if that popping is judged as insignificant, it is no problem. The fracture toughness is determined by point B, which is a complete fracture. Point B is on the slide. Here I'd like to talk about the previous study done by Willoughby in late 1990s. According to his study, the driving force of a propagating brittle crack in the standard bending specimen can be decreased by the reflected stress wave, which is generated at the specimen surface, especially at the lower jig. Here is an animation. When the crack originates, the stress wave will originate and reflects at the lower jig, and then have interference with the propagating crack. Okay, so therefore, a running crack which is small enough to be arrested before the reflected stress wave arrives will also arrest in real structures. So based on the experimental data, the maximum crack length of the unaffectedly arrested brittle crack in the standard bending specimen is just a 4% of ligament, and it corresponds to 5% of load drop ratio of a pin. It is said that the current popping judgment criterion is too conservative because there are two reasons. And one of them is that there's no experimental study due to the difficulties to produce a test specimen that can ensure the popping. And the second reason is that there's no consideration of difference of load mode of the CTOD test and real structure. In other words, it's bending and tensile. So the objectives of this study is to investigate of mechanism of formation of popping and improve the popping acceptance criteria. Alright, now let's move on to the experimental part of this study. Okay, here to observe in detail of the behavior of popping, we prepare a specially manufactured welded joint that can ensure the occurrence of poppins. So the NLLS, which is a very brittle material, is welded on the center of base metal and then covered by MGS80, which is a tough material. We prepare a section notch specimen, which is the reproduction of real weld with local brittle zone, and a surface notch specimen, which the brittle area is fully distributed along the crack tip. For reference. So during this presentation, it is very important to know that the tensile mode represents the load mode of real structures. In other words, the tensile represents the real structures. So we carried out the bending test and tensile test on both the section notch and surface notch of a standard specimen whose E0 by W is 0.5. And we also performed the tensile test on shallow section notch specimen, whose E0 by W is 0.3 and 0.15. And the test temperature is from 0 degrees Celsius to minus 60 degrees Celsius. And nextly, I will show you the results of the experiments. Okay, so here is the typical test results of a standard specimen. Showing the picture of fracture surface and the PVG curve. In all specimens, brittle fractures occurred, and the brittle cracks were all arrested in section notch specimens, while there are some surface notch specimens showing the complete propagation through the entire specimen. Okay, so here's a summary of the experiment. Firstly, the section notch and the surface notch are compared. It is on the left-hand side on the slide. There's no section notch specimen fractured completely, and there is some section notch specimens which had a low drop ratio of more than 10%, and some surface notch specimen fractured in brittle manner completely. And now let's move on to the right-hand side of the slide. It is comparing the standard CTOD test, which is a bending test in this experiment, and the shallow tensile test. Okay, so some shallow specimen at lower than minus 20 degrees Celsius fractured completely, and the maximum low drop ratio of CTOD test at that temperature was 21.4%. And then the shallow specimen at 0 degrees Celsius showed pop-in, and the maximum low drop ratio of that temperature was 16.6%. So based on the results of this experiment, it is inferred that it would be no problem to change the critical low drop ratio for pop-in judgment from the current 5% to new 10%. Okay, now let's move on to the analysis part. Okay, so to find out where the stress wave reflects, whether it reflects from the lower jig or the upper jig, or any other surface, and to see the difference of load mode of bending and tensile test, which is very critical to the improvement of judgment criteria. We carried out to the FEM analysis. The conditions of the analysis is shown on the slide, the left upper side. And we evaluated the driving force of a crack based on the KD value in front of the crack tip. We normalize the log KD value by Rhodes equations to see the behavior of KD value regardless of crack velocity. Okay, on the right side of the slide, I just put the result of analysis. That is the relationship of crack extension and normalized KD. Okay, so I want you to pay attention to the left graph, which is bending mode. The trend of KD of the bending mode is decreasing with crack propagation. And when the velocity of crack is more than 400 meters per sec, KD decreases more rapidly than the static solutions. On the graph, it is purple and the sky blue line. And on the other hand, the trend of KD of the tensile test is unchanged or slightly increasing. This is against experimental results because there's a fact that the arrest happens even in the tensile mode specimens in experiment. So here I'm showing the previous study done by Welded again, and here's animation of the reflected stress wave. So based on his study, because the amount of extension of the crack depends on the velocity, the KD behave like the graph on the left-hand side. However, the result of FEM analysis was on the right graph. It is completely opposite. So therefore, there is a misunderstanding of the effect of reflected stress wave. So now it seems difficult to describe the popping mechanism by the traditional theory, which is a theory by reflected stress wave. Yeah, it is not good. Okay, so here we suggest a new popping mechanism described by superposition of tonal clock model on FEM. It is a simplified model which consists of the superposition of KD obtained by FEM, which I described from the previous slide, and K of tonal clock shape model that is developed to simulate actual clock driving force of sectional specimens. The core part of this model is a consideration of the closure effect by the side ligament, which is an area drawn by the blue line. The closure effect of the side ligament is calculated by the equation on the slide, and this K closure 1 is the amount of closure effect come from this area. I mean, it is surrounded by the half circle line and the vertical and horizontal line. And the K closure 2 is come from this rectangle area. And it is very important to know, to understand this model, is that the difference of the minimum clock velocity of the tensile mode and bending mode. I mean, it comes from the theory of plastic strain, which is a completely different study from this study. But I mean, for here, I just want you to know that the minimum clock velocity of tensile mode is around 400 meters per sec, while the one of the bending mode is around, I mean, it's close to the static solution. And for this study, I put it as 10 meters per sec. Alright, so here is the result of this new model. The green line represents the sectional specimens, and because the sectional specimens which we prepared on the experiment, the width of the local brittle zone was 2 millimeters. And the blue line represents the surface notch specimens, meaning the whole area in front of the notch was the local brittle zone. And this is very important to say that this model can explain the actual experiment very well. So from this result, it is suggested that the brittle clock is more likely to arrest in bending mode than tensile mode in case of the straight clock shape. But 3D tunnel clock shape effect, which is a closure effect of the side ligament, really helps to enhance the arrestability in both mode, bending and tension. And it becomes clear that the local brittle zone width requirement is important for the popping clock arrestability when judgment condition in standards will be discussed. And here's a summary of this study. So according to the novel experiments, which induces pop-ins and a numerical model that is combined FEM analysis and simplified SIF calculation, it was revealed that the current requirement in major standards for pop-in judgment was too conservative. And the previous study of reflected stress wave done by Willoughby is not an appropriate theory to describe a popping clock arrest. And the popping clock arrest by the closing effect of the side ligament, which comes from the fact that the popping is a tunnel clock. The width of the local brittle zone is an important parameter for the popping standard. Our new proposal of the judgment criterion is that if the width of the local brittle zone is less than 2 millimeters, and the pop-in of less than 10% of the load drop ratio can be ignored. And we will propose this new criterion to ISO TC164 committee in future. Alright, that's it. Thanks for listening.